So the chain rule is actually one of the more significant sections. This concept is really important. All right, so let's consider y equals 6x minus 10. In understanding the chain rule, I don't want you to use the prime notation. I want you to think of it in terms of your dy dx. So if this side is y and this side is x, the derivative is dy dx, and it equals 6. We also see there's a GCF of 2. I could rewrite y as 2 times the quantity, 3x minus 5. Now say that I want to consider this a composite function, and I'm going to say, let's have u equal 3x minus 5, then y equals 2 times u. Now if I take the derivative of u, that's with respect to x. du dx equals 3. Now if I take the derivative of y, that's with respect to u, and that is 2. So what's the relationship to dy dx, du dx, and dy du? I can see that 3 times 2 equals 6. I'm going to put, let me do this. Let me say 2 times 3 equals 6. Where did the 2 come from? dy du. Where did the 3 come from? du dx. Where did the 6 come from? dy dx. And notice your du's cancel. So there's a lot of manipulation with chain rule. Sometimes it's manipulating your derivatives. Other times it's a little more straightforward. Okay, so let's consider y equals dy dx equals 36x to the third plus 12x dy du equals 2u du dx equals 6x. How do we get this? dy dx equals dy du times du dx. So dy du is 2u times 6x. But we have to be careful here. I don't want, if this says dy dx, all my variables on this side have to be in terms of x. So u, I have to come back here, is 3x squared plus 1 times 6x. All right, so probably what I would do, I'd take the 2 times 6 to get 12x. And then distribute 36x to the third plus 12x. And there we have that. So really be careful with your variables, because when I have u and x here, but I have just y's and x's, what this is telling me here, all the variables on the right need to be in terms of x. All right, so go ahead and copy this down. Your chain rule, this top part's a little extra. If you want to get, I've got room for it if you want to write it down. Otherwise, just get your chain rule. If you want to pause the video. Okay, so the application, we have x of t so what I do with this, we can do this a couple ways. I personally would rather just kind of move into, let's go to the next one and I'll come back to this. This is typically how I do derivatives, the inside out rule. So think about if we've got a composite function f of g of x, when we take the derivative of one part, the inside part stays the same, then we take it times the derivative of the inside. We call that inside out. So let's look at example 4, and the way I want you to think about this is we take the derivative of sine, which we know is cosine, the inside stays the same, times the derivative of the inside, 2x plus 1. So one of the ways you can think about this, you can take the derivative of sine, you can take the derivative of x squared plus x. Whenever you're doing the derivative of one, the other portion stays the same. Your trig functions have to be taking the trig functions of the same thing. So that's why, like back here, what I would do to get the velocity, the derivative of cosine is negative sine, and this portion stays the same, times the derivative of the inside, which is 2t. So that's how I would do that one. Okay, so here is a 3-link chain. I always think it as power, trig, inside. Power, trig, inside. If you notice g of t, whenever this is a function notation, I just use my prime notation. There's no power, so I do the derivative of tangent, which is secant squared. The inside always stays the same, times, now I'm going to link it together. I'm taking the derivative of the inside. So what's the derivative of 5 minus sine 2t? What's the derivative of negative sine, negative cosine? This portion has to match this, times, what's the derivative of 2t? 2. So we had to take the derivative of 3 separate things, linking it all together. Tangent was secant squared. The sine is cosine 2t, and 2t is 2. Now probably I would rewrite this, and I would take this 2 and this negative and put it way out front. And that would be my simplified version. All right, so we were talking earlier about you can sometimes use multiplication. dy dt equals dy dx times dx dt, where these variables match, so you can cancel it. We can also use derivatives, or division with our derivatives. All right, so let's consider, and what I want you to always think about is the slope comes from the derivative of y with respect to x. It has to be dy dx because when we graph, we're graphing it on an xy graph. So if we consider our derivatives here, this is dx dt Derivative of secant is secant t tangent t. The derivative of y, dy dt, is secant squared t. Now, we're missing, this is at t equals pi over 4. If we want the equation of the tangent line, we need two things. Point and slope. To find my point, I need the x coordinate. So x equals secant of pi over 4. So let's remember, pi over 4 is just 45 degrees, 1 square root of 2. Secant is the reciprocal of cosine, so that's square root of 2. Then y equals tangent of pi over 4. Tangent is y over x, which is 1. So the coordinate point I'm going to use is the square root of 2, 1. My slope is dy dx. This is the important part. This is where we find dy dx by taking dy dt divided by dx dt. All right, so we need dy dt is secant squared. Dx dt is secant tangent. So this secant cancels out one of these secants, so it ends up being secant t over tangent t. Well, we just found secant t right here. That's square root of 2. And we found tangent of pi over 4 here. So my slope is the square root of 2. So my equation, y minus 1 equals the slope times x minus the x coordinate. So you can just write this chain rule down. You can, so when we're taking the derivative of a function, technically, we take the derivative of the function times the derivative of the inside. Okay, so let's come back to our power trig inside. So dy dx, we have to do the power first. Now this is really important. When you do the power, nothing else changes. Oops. Five sine to the 4th x. This is the power. The trig, you're only taking the derivative of the trig. That's just cosine of x. Power trig. And the inside is just x, and the derivative of that is just 1. Find the slope of the tangent line where the curve at the point where x equals pi over 3. So the slope of the tangent line is just m. We have the dy dx, so that means I can just plug in pi over 3, 5 times. Now remember, we're taking sine of pi over 3 to the 4th times cosine pi over 3. Pi over 3, 180 divided by 3, 60. 1, 2, square root of 3. Sine of pi over 3, square root of 3 over 2 to the 4th times cosine pi over 3, 1/2. All right, so let's just take the 5 times 1/2 to get 5 halves. When I do this to the 4th, radical 3 to the 4th, it's easier to see this one all written out. Radical 3 times radical 3, 3, times radical 3 times radical 3, 3, and 3 times 3 is 9. Then we have 2 to the 4th, which is 16. And when we multiply, we get 45 over 32. That's letter A. All right, last one. I'm going to go ahead and clear this. As soon as you get that copied, you might want to pause it because I'm going to clear it for letter B. Show that the slope to this function is positive. So remember, our slope is represented by dy dx. What I'm going to do now, in the past, whenever we have this little fraction, we have to use quotient rule. But now we have the chain rule available. So what I'm going to do first, I'm going to move this up, and we have 1 minus 2x to the negative third, and that makes the whole process easier. We no longer have to use quotient rule. If you have something in the bottom and a constant on the top, it makes it a whole lot easier. So now dy dx, power first. When we do the power, nothing on the inside changes. Bring the power down, subtract 1 times the derivative of the inside, which is negative 2. Now, I'm going to put my negative exponent portion back into the denominator. Once I move it back down, it becomes positive. Then negative 3 times negative 2 is 6. Show that it's always positive. My numerator is always positive. I have an even power in the denominator. Therefore, m is always positive.